Welcome. In this explainer, we're going to uncover some of the hidden physics behind your everyday electronics. We'll connect the dots between something as simple as a dying battery and, believe it or not, why birds can sit on a high-voltage wire.
Okay, so let's just dive right in with a pretty simple question. Why isn't this bird getting totally zapped? And what on earth could that possibly have to do with the batteries in your TV remote slowly dying? Well, it turns out the answer to both questions is exactly the same.
To solve this little mystery, we first need to take a look at a secret that every single battery is hiding.
You know how every battery you buy has a voltage printed on it, right? Like 1.5 volts or 12 volts? Well, in physics, there's a fancy name for this, electromotive force, or EMF. But here's the secret. That's the ideal voltage. In the real world, you almost never get that full amount of power.
So that leads to the obvious question, right? If the battery is rated for 12 volts, why does the thing it's powering always get less than that? Where does that energy just vanish?
Well, the culprit is something called internal resistance. You can think of it as the hidden villain that lives inside every battery, and its job is to quietly steal a little bit of its power.
So here's what that looks like. On the left, you've got your perfect, ideal battery from a textbook. But on the right, that's reality. See that little zigzag symbol inside the battery box, the one labeled R? That is the internal resistance. It's kind of like a tiny obstacle course that drains some of the battery's energy before the power even gets a chance to leave.
You know, a really good way to think of it is like a tiny, unavoidable energy tax. The battery literally has to pay this tax on its own power, just to push the electricity out. It's basically a bit of internal friction that turns useful energy into wasted heat.
And this is the key to understanding why batteries get so much worse as they get older. It's not just that they're running out of juice, they're actually fighting against themselves more and more.
Just look at the difference here. A brand new battery has a really low internal resistance. The energy can flow out nice and easy. But as it gets old and the chemicals inside break down, that resistance skyrockets. The path for the energy gets all clogged up, and that starts to choke off the power. So when our battery is new, with that low internal tax, it's delivering a really healthy 46.3 watts of power. Everything's working just as it should.
But look what happens near the end of its life. With that much higher internal resistance, it can only squeeze out 17.3 watts. That is a massive drop in performance. And that's exactly why your flashlight gets dim or your remote just stops working, even if the battery isn't technically empty yet. Okay, so this whole idea of resistance doesn't just apply to what's going on inside a battery. It's also absolutely fundamental to how we connect things together in any circuit.
So check this out. When you wire things up one after another, like these two light bulbs, we call that wiring in series. And when you do that, their individual resistances just add up, which makes it harder for the current to push through the entire circuit.
But you can also wire things in parallel, like you see with these landscape lights. This gives the electricity multiple paths it can take. Now, this is usually more efficient, but a whole new problem can pop up. The resistance of the wire itself can start to cause trouble, especially when you're talking about long distances.
And this is a perfect real-world example of that. Because that long cable has its own resistance, the voltage slowly drops bit by bit along its entire length. So what happens? The lights that are closest to the power source are nice and bright, but the ones at the very end of the yard are noticeably dimmer.
All right, we've got all the pieces of the puzzle now. Internal resistance, series and parallel circuits, voltage drop, we have everything we need to finally solve our original mystery about the bird.
The final key, the master rule that governs pretty much everything we've been talking about, is Ohm's law. It's a really simple formula. Voltage equals current times resistance. It's one of the most fundamental rules in all of electricity.
So let's go back to our bird. A high-voltage power line is engineered to have extremely low resistance so it can move electricity super efficiently. Now, the distance between a bird's feet is tiny, right? Maybe a couple of inches. So that means the resistance of the wire between its feet is practically zero.
And according to our good friend Ohm's law, if the resistance is practically zero, then the voltage difference, the voltage drop, across the bird's body is also practically zero. Look, electricity is lazy. It always takes the path of least resistance. The wire is a superhighway, and the bird is a bumpy, high-resistance dirt road. The electricity just ignores the bird completely and keeps cruising along the wire.
So, in the end, that one simple concept, resistance, explains both of our mysteries. It's why your batteries fade, and it's why birds can chill out on a power line. It's just a fundamental force quietly at work in the technology all around us. So now that you know the battery's secret, what other everyday tech makes you wonder?